Hey there, here I am with Exam 3. I'm going to go over Exam 3. Here's the version of Exam 3 I have. Here's a question number one. Question number one about the equilibrium strongly favors products, right? And so products over reactants, if we do K is products over reactants, then the one that favors products has a very large numerator and a very small denominator, and so the answer is that the value of K is much, much greater than 1. Number 2, equilibrium constant for the formation of hydrogen iodide from hydrogen and iodine is 45. So that's saying that K is equal to 45. Okay. And says at a certain temperature, the following is true regarding this equilibrium. So luckily for this version of the exam, it's actually right next to this question. And so since K is greater than 1, 1 has to be true. The reaction is product favored. And since it's product favored, 2 cannot be true. So we can remove any of the answers that have 2 in them. And that leaves us with C, D, and E. And since it's product favored, the equilibrium is going to lie to the right. And so we're looking for things that contain 1 and 3. And so the answer is C, 1 and 3. Question number 3. If the reaction quotient Q, so we're questioning equilibrium, has a larger value than the related equilibrium constant, so we're saying Q is greater than K, what's going to happen? Okay, and so if Q is greater than K, then we can look back up again here at this equation we have here, which means there's more products than there's supposed to be, or there's less reactants than there's supposed to be. Both of those are probably true, which means that we've gone too far. When we're questioning the equilibrium and it's too big, we've gone too far. So that means the reaction will consume products and make reactants, because it can't be at equilibrium. The value of K doesn't change. Okay, and we're not talking about heat at all. So we had two choices, go forward or go back, and since Q is too big, we have to go back. Alright, here we are for page 2. Page 2 has a very large picture at the beginning for this question, and it's asking where is the energy profile where the transition state happens. And so luckily for us right here, it's in A. Is where that is, and so it's asking for which one is A. So the transition state is the will they won't they moment between the bond forming or breaking, and it's at the top of that activation energy peak, and so the answer here is A. Moving on to question 5, which of the following is true for a chemical reaction at equilibrium? Okay, and so it's again asking about equilibrium, and so when equilibrium is happening, we have concentrations. We have concentrations that are not changing. And so the concentrations are the same. Okay, it doesn't mean that they've stopped. It means that they're not changing. And so B and C has to be false. Those cannot be true. Okay. And so that leads us to, and E is also not true. And so it leads us to two things, A and D. The rate constants for the forward and reverse reactions are equal, or the rates of the forward and reverse reactions are equal. This is another one of those definition problems. A reaction is at equilibrium when the rates of the forward and reverse reactions are equal. The rate constants do not have to be equal, but the rates have to be equal. Question number 6, for the reaction given here, it's asking to compare the rate, of iodine consumption to the rate of water production. Okay, and obviously there's going to be a difference in sign here because one is being consumed and one is being produced. However, what we need to compare is the iodide and the water. And so to make those rates equal, we'd see that the 1/3 the rate of I minus has to equal 1/2 the rate of water. And so that's the case. And so now if we're saying when we have the rate of iodine consumption is blank that of the rate of the production of water, we want to isolate the production of water. And so we need to divide both sides by 1/2. Dividing both sides by half is essentially multiplying both sides by 2. And so 2/3 the rate of iodide is equal to the rate of water. And so the answer is A, if we do the math correctly. And if you look at that question, here there's a 3, so that's going away faster than this is showing up. And so when we do the multiplication here, 2/3 of iodine slows down that rate so that the rate of water is smaller than the rate of iodine removal. In this problem, we're looking for the energy needed to form an activated complex. That activated complex, also called the transition state, is the energy needed to form that transition state is the top of that peak from the question prior. It's the activation energy. And so the answer there is A. Number 8, the linear form of the Arrhenius equation is very useful as a plot of blank allows us to calculate the activation energy and the frequency factor. And so this equation was right on the sheet, and it's the log of the rate constant versus the inverse of the temperature, because that gives us the line 1 equals mx plus b. And that linear form is ln of k is equal to the negative e a over r times 1 over t plus the ln of a. And that's right from the sheet, and you can find that in the book as well. And so here is your y variable, here is your x variable. And so it's y equals mx. And so from that plot of the natural log of k versus the inverse of the temperature, you can get the activation energy and the frequency factor. So the answer there is A. Number 9. Which of the following statements regarding equilibrium constant is not true? So we need to make sure we're getting false statements. Okay? When K is much, much greater than 1, the concentration of products is much greater than the concentrations of reactants. That is true. That is something that's very true. In fact, that was question number 1 on this version of the exam. When K is equal to 1, concentrations of products and reactants at equilibrium are equal. That is the definition of when some numerator and denominator equal 1. Right? Equal each other, then we have 1. Whether that's 1 over 1 or 3 over 3 or a million over a million, that is the definition. So that also has to be true. When K is equal to 1, the forward and reverse rate constants are equal. That is also not true. D, when K is much, much less than 1, the concentration of reactants is much greater than the concentrations of products. Okay, that is also true. That's the inverse of A. And so since A is true, D also has to be true. So one of the things I didn't talk about in C there is that the forward and reverse rate constants are equal. No, it's just the rates. And that was a previous question earlier. So when K is equal to 1, the forward and reverse rates are equal, and that would be true. But it's also true that the constants are equal. So again, that is true. So that leaves us with only one answer. E, when K is much, much greater than 1, the products and reactants come to equilibrium rapidly. That is not necessarily the case. This is chapter 14, equilibrium. I had no idea and no information about how that reaction happens. And so K can be much, much greater than 1, but a very slow reaction. And so chapter 14 and the word rapid have nothing to do with each other. And so the answer there is E. Moving on to question 10. Which of the following must be true of an intermediate in the reaction mechanism? And it turns out that both 1 and 2 are true. It has to be produced in one step and consumed in another, for that's the definition of an intermediate. It is never included That is not true in the net reaction for the mechanism because it is an intermediate. So that's the definition of an intermediate, and so that answer is D. Number 11, the reaction there seems to follow the rate law where it is second order with respect to NO2. And it is second order because of that exponent 2 there. So we're asking, is the following a valid mechanism and why? And so we have these two steps in this mechanism, step 1 and step 2, and we're asking, does that mechanism, those two steps there, match the rate law? And that's what the question is asking, very similar to one of the homework questions. And so when we are evaluating whether a mechanism is valid or not, we look to the rate determining step. And so the rate determining step must be presented in the rate law. And the rate determining step is the slow step, and the slow step has two reactants, NO3 and SO2. There is no SO2 in the rate law that has been proposed here, that has been followed. Oh, and since that is the case, this cannot be the answer, and it's no because the derived rate law does not match the experimental law. Okay, and so when we do that, it can't be the case. Now, it's not because NO3 is not there, okay, because that is true. D is true. It says NO3 cannot appear in the mechanism. So, since NO3 is an intermediate, that's why it's wrong. But NO3 can appear in the mechanism. It's an intermediate. See question 10. The reason it's wrong is because this, which is not an intermediate, does not appear in the rate law. And since sulfur dioxide is not in the rate law, that is not a valid mechanism. Okay? The derived rate law does not match the experimental elementary step or the experimental law. And then for the last one, we have that an equilibrium expression talking about calcium oxide, sulfur dioxide, and calcium sulfite. Two of those three are solids, so they wouldn't enter into any equilibrium expression. And it's asking again for that equilibrium expression. Products over reactants. Sulfur dioxide is a reactant, and so the answer in terms of concentrations is 1 over the sulfur dioxide concentration. All right, here we are now into the problems part of the exam, and we're talking about a thermal decomposition occurs by the following reaction measured over 5 minutes. And so minutes means time, which means we're talking kinetics. The other thing that tells us we're talking for kinetics is we're talking about rate laws, and we're talking about orders. So we're presented with these three graphs here, having several things on the y-axis. Concentration versus time, the ln of A versus time, and 1 over A versus time. The concentration on the y-axis, time all on the x-axis. And so these are all the same data for the concentration of this reactant going down as a function of time. And so if we draw the line in here, we can see that that's the data when we do the concentration of A. These lines, these points here on this graph fit on the line. And then for this last one again, when we take the 1 over the concentrations, we see that that also does not fit the line. So the one treatment of the data that makes a line from the points is indeed this one. And so when we look at the integrated rate law for a first order reaction, we're plotting the natural log of the concentration versus time. And so that means that this reaction is a first order reaction. And so we found out now that first part, it's first order because it produces that straight line. And so the rate law for that reaction would be that rate is equal to K times the concentration of our reactant, C2H5Br. One of the other things that is sort of a giveaway, even if you didn't know how to do this problem, that this is a first order reaction, is that there is only one molecule that's being decomposed here. And so by its very nature, it needs to be a first order reaction. It's just decomposing, and so we have a first order reaction. And so in terms of the words to justify that, you can say that it's only one molecule, or you could say that the treatment of the natural log of the concentration versus time produces a straight line to give you that rate law. For the second part of this equation, you have these graphs, and I mentioned that you do not have to have the correct answer to part A to receive full credit for part B. And so in part A, if you had come up with some other order, a second order or a third order, or some other order for the equation, you could have figured out the rate constant. But since it is a first order rate constant, this is going to have slope of negative k, and so negative k equals negative 0.8837. And so negative k is that, so that means positive k is 0.8837. And so in terms of the units, if I go back to my rate law, the rate for this reaction is the concentration over time is equal to something times the concentration. That means the units of k here have to be 1 over time. And so for this here, we have 1 over time, and so our unit is time, is in minutes, and so this is in inverse minutes. Excuse me. All right, on to the second question. There are many reactions involving nitrogen oxygen and nitrogen oxides at high temperature. We have the following equilibrium constants. And so here we are, we have these two reactions, and we need to manipulate them to find the value of this reaction. And so we need to combine reactions until we get this reaction. And so that's our final answer, so to speak, our reaction 3. We want to know what is the equilibrium constant for reaction 3. And so we can do a couple things looking at reactions 1 and 2. First off, with reaction 1, we can see that the dinitrogen tetroxide, the N2O4, is on the left-hand side. And so the first thing we need to do is flip that reaction. And so when we flip that reaction, it becomes 2NO2 in equilibrium with N2O4. So that when we add those reactions, we get N2O4 on the product side of the reaction. And so since we flipped the direction of that reaction, our new equation is now going to be 1 over K1. We've made products reactants and reactants products, and so we're going to have a value. I don't have any numbers yet, but that would be 1 over K1. For the second part of the reaction, we've now settled out what we need on the right-hand side. We need to deal with the reactants in this overall reaction that we're trying to get, and we also need to, since we're here, we need to cancel out those reactants. And so we have this K2, and K2 in its form, where we have half an N2 and an O2 going to 1 NO2, we actually need that reaction twice. And so when we have that reaction twice, this 2 will cancel with those 2. And when you add up the 2 halves, you'll get a 1. And when you add up the 2 1s, you get a 2. And so we have now canceled out all the parts. This is equation K2. This is equation K2. And so by adding those 3 equations, we can get the equation we want. Now, when we're combining equations, when we add equations, we multiply the k's. And so the value would end up being K2 times K2 over K1. And so you just plug in the values here that you have for K1 and K2, and you're going to get numerically the correct answer. All right, on to problem number 3. we're presented with this equation that has a Kc, and we're told to calculate Kp. And so we have this equation that relates Kp to Kc. And so we have Kc at 0.078. We have R, which is 0.08206, which is the one we use when we're talking about gases. And since Kp is K with respect to pressures, we're definitely talking about gases. We have to put the temperature in there, and this is at 700 Kelvin, already in Kelvin. So the only thing we really need to figure out for this problem is that delta N. And whenever we do delta, we do final minus initial. And so it's delta N is the change in the number of moles. And so here in this equation, we have 1 mole of sulfur dioxide and 1 mole of chlorine gas, and 1 mole of the SO2Cl2 as the reactant. And so final, or products, we have 2 moles. Initial, we have 1 mole. And so 2 minus 1 is 1. And so all we need to do is multiply 0.078 times 0.082 times 700, and we get a number that is 4.46 for Kp. Moving on to part B. Again, this is another question where we don't need the answer to part A to answer part B. And so we're asking, is this reaction at equilibrium? And so if are we at equilibrium? Are we there yet? We're going to calculate Q. And so Q in this equation would just be the products over the reactants. And so that is the concentration of SO2 times the concentration of chlorine gas in the numerator and the concentration of the reactant in the denominator. And so all we need now is concentrations. What this problem gives us, however, is moles. Moles of this and moles of that and moles of that. And so in order to get concentration, we need to do moles per liter. And so this flask contains all of those moles. And so the denominator, the liters, is the same for all 3 of those. And so what we end up with is 0.46 over 5.5, 0.008 over 5.5, and 0.04101 over 5.5. And we do all that math out, and that gives us 1.63 times 10 to the minus 3. That is much less than the Kc, which is 0.078 from the top of this page. And so we're comparing Q to K, and when we compare Q to K and it's less than, the reaction still needs to move forward. And so the answer is that the reaction will proceed in the forward direction. Last problem is a similar problem to the problem from the last exam. We have these 3 trials of experiments, and we're changing the reactant concentrations and seeing how that affects the rate in molar per second. And so determine the rate law for the reaction. So again, we're talking about how fast this reaction is. And so we're going to have to find out the rate is equal to K times the concentration of H2 raised to some exponent and the concentration of ICl raised to some exponent. That's what we're trying to find out, is what is X and what is Y. But that's the basic rate law, and you would have gotten partial credit just for writing that down when I'm asking for a rate law, because the only things you're missing there are the X and the Y. And so how do you determine the X and the Y? Well, you need a set of experiments where one part doesn't change, but the other part does, and then another part where this part changes and this part doesn't change. And so you have those 2 sets of reactions where you can have something changing and something not. And so in experiments 1 and 2, we're changing the ICl concentration. And some of you did, going from experiment 1 to experiment 2, you're decreasing by a certain factor. And some of you said, well, I'll just start at experiment 2 and I'm increasing by a certain factor. And so going from experiment 2 to experiment 1, I'm increasing the concentration by a factor of 4. And so I increased the concentration by 4. What happened to the rate? Well, if I take 0.335 and multiply by 4, I got an increase of the rate by 4. And so if it's a linear change, which means whatever I do to the concentration happens to the rate, that is a first order. And so we've just found that x here is equal to 1. And so we can either write the 1 in, or we can leave it out like we normally would for exponents equal to 1. For the next one, for experiments 1 and 3, we're leaving the ICL concentration the same, but we're changing the hydrogen concentration. And again, if we look at 3 versus 1, we're changing it by 5 times the concentration. What happens to the rate? Well, 1.34 to 0.268, that is a 5-time change. And so this is also a first order equation with respect to the ICL. So overall it is second order, but each of those is first order with respect to the concentrations. It then asks you to calculate the rate constant for these data. So you just pick one experiment and say that 1.34 is equal to K times 250 times 324. Okay, and so the only thing you don't know there is K, so you can solve for K. I did not take off for units in this problem, as you can maybe see in your graded exams. I forgot to change these numbers from torr to torr per second for the rate, so there's a bunch of other things that I'm just not counting there. Again, you don't need B to calculate, you don't need A correctly to calculate B, so if you had come up with some other rate law, you could have solved for K. As long as you were consistent in how you solved for K, you got full marks for part B. In part C, it's saying, okay, now that you have that K, from there, calculate what happens when H2 is 80 and ICL is 100. And so it's asking for that. Okay. Again, this is another version of the same problem from the second exam, where you had to determine the rate law, the rate constant, and then the new rate at a different thing. And so you can grab the number that you just solved for in part B here and put that in. Again, you do not have to have B correct, but you need to know what a rate law is so that you can be consistent with how you're treating that. And you can solve that, just because this is now the only thing you don't know. And so you can multiply those three values that you have and get the correct answer, and the correct answer should be in molar per second, because that's the unit for rate up here. All right, so there's the exam gone over. Next exam is April 29th, which is a Wednesday, coming up right before the end of classes. Don't forget to go to the tutors. Come see me during my office hours. If you can't make my office hours, please send an email. Come by. I'm here a lot. I would love to talk to you about the course.